Recording in progress.
Let's go to the website. All right, so you should be seeing the course website. Here's the deep learning calendar. It should be updated. So we are currently in this last stage, right? So semester, we started with fast AI. We did some image processing, transfer learning, etc. Standard ResNet. Then we started with transformers for text. And we looked at transformers for sequence and token classification, which were basically both supervised. So the classic example here is like sentiment analysis for sequence. And for token would be like named entity recognition of part of speech tag. So we looked at that. Then we looked at fine tuning for text classification with your own data. And I always put this link here because this is that Turkish data set. Did that. Then last week I went over BERT, and we started with what word embeddings are, like the classic word to vec. I mean that's kind of how the paper runs, actually, the original BERT paper. So I went over word embeddings. Then we talked a little bit about encoders and how BERT is basically a very powerful encoder. So the videos I think are up to date. And then BERT pre-training tasks. So I talked about how BERT trains on two specific tasks, which are mask prediction and next sentence prediction, right? And so those were kind of interesting there. Then what we have left, so today is April 4th. So I want to stress a couple of things. So April 25th, you guys will do your presentations of both your project and your GPT homework. So we'll just take that time to kind of discuss that. And then I'll do a course wrap up of any topics that we have left. Today, we're going to cover transformers for semantic text similarity. So I'll basically jump into the code for this first. So we'll just do some interesting things in the code. This runs actually on CPU. So I tested this on my Windows machine here, and they all ran nicely. So no need for the GPU here. But we'll talk about this. This would be where, a good way of thinking about it. If this week was supervised learning, you could think of it a little bit as this is unsupervised learning, a little bit. All right, but it's really about semantic similarity, and I think you'll find it interesting. We'll go over that code. Then, as you can see in the second half of today, I will go over Roberta, and basically I'll just bring up the three papers, BERT, Roberta, and the biggest Roberta I've seen so far. So kind of to emphasize how, a few things I have learned about them. But really, if we understand BERT, we understand Roberta. Roberta, I think BERT is Google, and then Roberta is Facebook. All right, please, I remind you next week, Monday, I'll be out of town, so you'll just have your exam. I will post it on Brightspace. It'll be an exam. It'll open up at 2:30, and you can work on that until 3:50. And then after that, just work on your term project. Okay, you can email me, and then we can Zoom anytime during that week. If on Wednesday, after Wednesday, Thursday, Friday. If you guys have any questions on the project, but just use it as a project day to work on the project or GPT. And then I have left April 18th and the 20th open. Roberta is kind of the end of BERT. I mean, there's more things. I heard there's like a Luke and a Hubert now or something, but I think that's good enough as far as Roberta. So probably this week I'll either cover, I have a few ideas just the next chapters from semantic text similarity. There's a little bit there, or GPT, or vision for transformers. So we'll keep that as a miscellaneous. I have to decide what I think is, probably good. And so, but that's really the last week. So we'll do a lecture lab on this day, and then, as I said, your presentations. So are there any questions about the schedule? Any doubts? Any confusion?
What do you think will be on this exam that will be different than the final?
I always change them a little, but they're comprehensive. So it's just a way. It's easy points for you guys. Just to do I'll change the questions for sure. I can say this exam will probably have a lot of information on BERT. And then the final exam will have information about your presentations and whatever I cover here. Plus, I could go back to fast AI, image processing, where I think this exam will mainly focus on BERT, just because that's more in my head right now. Does that make sense?
Yeah.
I do think understanding BERT is really important. That's why today I'll point out the 3 papers that I think are the most important. Probably April 18th, we'll go over the paper for GPT, which I have here somewhere, but we'll get to that. And then vision transformers is the one topic I'm trying to, but I don't know if I'll be ready for that. So we'll see. Okay. Any other questions? All right. I'll certainly point out the paper for vision transformers. So it's a paper that Jean LeCun, who's the chief scientist at Facebook, Facebook AI, he shared it the other day, and so he had some thoughts about it. So certainly it's worth a look at, as that would be in direct competition with ResNet CNNs that we learned in fast AI, right? So somewhere over here. Okay, so let's go ahead then. So I think that pretty much the most important takeaway is April 11th. Please remember this week, it'll just be the exam and work on project. So there won't be a Zoom meeting, just Brightspace link. I'll be monitoring my email at the time, but just, I'll be at a place, so it may be a little bit difficult. All right, so I think that's it. So let's go ahead then. For this topic, let me open, but now, of course, the code, as usual, is already on the GitHub, so you can just get it from there if you would like. It's going to be under the Hugging Face Transformers, and I created a new folder called Embedding Sentence Similarity. Okay, I think it's an actually very important topic. It's something that I believe you will need at some point. So it's certainly important to know about. All right, so today's topic, so the first half of today, and then the second half will be Roberta. Yeah, so let's get started. So the name of the topic today is embedding approaches, basically, for sentence similarity. Well, if you remember, last week I said that BERT is basically a very big embedding machine, right? So it's got an encoder architecture. This is the original BERT from Google. The history is really nice. The original mechanism, attention, no, the masking, attention, I actually don't know the history, but what a procedure called a masking procedure that, that we put in the mask and everything, at least it originates to Taylor in 1953. So that's what I always love about this is like all the, you think that everything's so original, right? And well, the idea was created in 1953. So. Anyway, so BERT is a giant encoder. It takes inputs of size 512, which could be one sentence and another sentence with a separator. So we talked about all this. Or it can be one single sentence, right? So there's problems that are for two sentences, like question and answer, entailment, that kind of thing. Or it can be just one sentence. Also, next sentence. So like this is the current sentence. Is this the next sentence? Right. And then it goes through a whole bunch of encoding layers. And then it comes out here. We remember this is the context for the whole, because the one that corresponds to the first token, the class, is the encoding. And then here we have the individual encodings for all the tokens, the words. So it's a giant encoding machine in a way. Not necessarily better than Word2Vec, but certainly it's been shown that it's good for specific tasks that it's trained on. So if it's trained for part-of-speech tagging, those embeddings are optimized for part-of-speech tagging. But that's after the fine-tuning. Remember that in the pre-trained, it's more generic. So the generic pre-trained encodings may not be as good as something like Word2Vec or Glove or something like that. Okay, so just be aware of that. I don't want to say that this, just because it's newer, that it's better than those mechanisms. All right, so we talked about this. So that's why the topic then today is called embedding approaches for sentence similarity. So what you can see is our goal here is we have sentence one, and then we have sentence two, right? The original ones, they get encoded. So these are, let's say, the embeddings, one, embedding two, and they usually have the same dimension here, n, let's say. And then they need to go into some type of a function, right? Something like the cosine similarity, etc. And this is just going to tell us how close they are. But the embedding can happen in multiple ways, including through BERT, or even better, through a fine-tuned BERT for sentence similarity. Do you guys see that? That makes sense? All right, so I'm not hearing any questions, so hopefully that means you guys understand. So what are we going to look at for embedding approaches for sentence similarities? So this includes, for today's topic, I mean. So for today, we're going to cover Glove, which Glove, I believe, if I remember correctly, was done at Stanford by, forget the name of that guy, one of the big ones, an NLP at Stanford. What's his name? Yeah, Manning, Christopher Manning. Yeah, Chris Manning, right? Dan Jarofsky, but I think it was Chris Manning. So he's like one of the top. He has made many contributions, particularly to NLP. I believe they worked on this, if I'm not mistaken. All right, so that's Glove. Then we're going to look at GRU. I think it's pronounced GRU. All right, these are all for sentence, let's call it semantic similarity. And they're a type of unsupervised. Then we have, so these are the, let's call them like the traditional classic non-transformer based models. And then, but as you might imagine, the idea is to compare to the new. So the new would be, so I'll change color here. And so the new techniques are based on BERT. and also SBERT, which is a specialized one. And then finally, Roberta, actually, but a fine-tuned Roberta. So a fine-tuned Roberta for sequence classification. And in particular, this would help us, the labels would be basically, it's a supervised approach. So it would tell us if something is neutral, contradiction, or entailment. So neutral, contradiction, or entailment. Okay, and as you can see, that also has to do with similarity. As a contradiction says, well, if something is contradictory, then it's not similar, right? Okay, and then entailment. An entailment is a deduction or implication that is something that follows logically from or is implied by something else, which, is similarity too, right? So in logic, an entailment is the relationship between sentences whereby one sentence will be true if all the others are also true. So it's a type of similarity, but just, classification versus these are more distance metric type of approaches. And then the other one is more of a labels and classes kind of a thing. All right, so that's the basic idea for today, is to kind of do this. I have, so we're going to create a script. And as you can see, the script is already on Brightspace, but we're just going to code it up. I'm just going to use my Windows machine should work fine for this one. Shouldn't be such a big issue. So let's go ahead and I need to start Jupyter. Or let me think about this actually. Because it's got a lot of live. Actually, I'm going to do this on the terminal. Yeah, let me just do this on the terminal. So I'm going to use so I'm just going to use the Anaconda prompt. All right, that should do it. So let me share that screen. All right, so you guys should now be seeing the screen. So let me do conda environment list. And so, yeah, it's probably PyTransformers. So I'm going to do conda activate PyTransformers. All right, there we are. Then I'm going to, window. I'm going to go to desktop. And I'm going to go to 530. Okay. And then, teaching in class. Okay. BIR. Okay, I don't have anything in here. Now we don't need a data set. Instead, we're just going to create a data set manually. And it's going to be in some kind of a list, so you guys could easily just bring it in from a text file. This one's easy as far as that, at least. So let's go ahead and since there are no files in here, let's create a file. I'm gonna call it embedding semantic text similarity BERT.py. Let's just say in class, just so I don't confuse this with other scripts that I write outside of class. All right, so does Nano work on this thing? Nope. How do I write this? I think Notepad, huh? Yeah. Hold on. Let me. Yeah, sorry, I'm gonna have to do this on Windows. I'm creating the text file. All right, so I have to type it again. So embedding semantic text similarity BERT in class. And this is going to be .py. Okay, and then I'm going to open this up with Notepad++. All right, so that should do it. All right, so now I'm going to share screen here. All right, so you guys should be seeing the prompt. And now if we use dir, you can see that the script is there, right? Okay, so we should be ready to run it. So let's go ahead and think about what we need. So this is going to be sentence embeddings and semantic text similarity. Okay. So for this, we're going to need some libraries. So we're going to need, for this to work, you need to install the following. So I'll just copy this. All right, and that's so you need to do once you've created your Anaconda environment. Let's say you built it from scratch using like Python 2.7, 3.7, right? You will need to install Torch, the transformers module from Hugging Face, Protobuf, sentence piece, which is this. Sentence transformers, data sets, and also Flare. Flare is actually Facebook has a library. And so that's what we'll be using today for some of this work. Once you've installed, once you've done pip install on all of these, should be ready. You can go ahead and invoke some of the libraries. So we're going to need import. I'm just going to copy this. So now we're going to need pandas. All right, so we're gonna import pandas as PD. We've got Torch. Apparently, I have it twice there. Oops. Then we have NumPy and then Flare, right? So from flare.data, import sentence. Okay, so that'll help us to process things. Okay, then after that, we're going to need the data. And basically what we're going to do is we're going to be comparing sentences, right? So that's our goal. So we need that. So we're going to have some examples of similar sentences. Examples of similar sentences. Right, and you can see here we have pairs of sentences. So these are examples of similar. So for instance, a black dog walking beside a pool should be similar to a black dog is walking along the side of a pool. A blonde woman looks for medical supplies for work in a suitcase. The blonde woman, notice the spelling changed a little too, is searching for medical supplies in a suitcase. A doubly-decker red bus driving down the road. A red double-decker bus driving down a street. There's a black dog jumping into a swimming pool. A black dog is leaping into a swimming pool. The man used a sword to slice a plastic bottle. A man sliced a plastic bottle with a sword. All right, so those are examples of similar ones. So at this point, we should be able to run this. Let me go ahead and save it. And you guys should be able, you guys can see the prompt, correct?
Yeah.
Okay, great. So then let's go ahead and just type Python, and this should run. All right, and there we go. So we convert this into a pandas frame. You can see we've got sentence 1, sentence 2, 4 examples, and then we've got the text there, all the sentence pairs. All right. So that's the, we create a pandas frame of similar. And then we just say that we want the columns to be sentence 1 or send 1 and send 2. Right? So that's basically the idea. Now we're going to need examples of the similar. I'm going to go ahead and copy that. We're just going to grab the similar sentences. Control V. So here we have some examples of dissimilar sentences. Again, we have a pandas frame to print it out. We print out dissimilar with send 1 and send 2. So here we're saying a little girl and boy are reading books. An older child is playing with a doll while gazing out the window. So those are dissimilar. 2 horses standing in a field with trees in the background. A black and white bird on a body of water with grass in the background. 2 people are walking by the ocean. 2 men in fleeces and hats looking at the camera. A cat is pouncing on a trampoline. A man is slicing a tomato. A woman is riding on a horse. A man is turning over tables in anger. Right, so these are examples of pairs that are dissimilar, okay? So that's what we want to now process through some of these mechanisms. So the next thing we're going to need is we're going to need a similarity function, okay? So we're going to copy this one. Okay, so this is our similarity function here. All right, so if you notice the similarity function, let me save, takes two inputs, basically sentence 1 and sentence 2. And it's going to use the cosine similarity function to measure the the difference. So the cosine similarity is a function that measures basically the similarity between two vectors, right? Embeddings are vectors in a vector space. So we'll be able to do that. So if you notice, the function comes from PyTorch, and it's just cosine similarity between S1 and S2. And it returns an object, so then we just need the item function to get the value, sim. And then we're going to round sim and also just show like 2 digits of it, okay? So then that gives us the number. What's important here is that we receive S1 and S2, the 2 sentences, not as the sentences in text anymore, but first they have to be embedded. Okay, so we have to send embeddings of the sentences. And then once we have them, we're going to take S1, we're going to take its embedding. And then from its embedding, we're just going to do unsqueeze, which if you remember, was just a function that we learned about to shape the dimensions of tensors, right? For the specific operation that we want to do. So you can always just print this out before and after the unsqueeze, just to see the shape of the embedding. Usually, it's pretty much that. So we've got the similarity function, but obviously we need embeddings and everything, and that's where the functions glove, grew, and all of them come into play, because they will be doing that work for us, that heavy lifting. Let's go ahead now. We've got the similarity function. The next thing we need is the evaluate function. So this function is the one that actually calls sim with the embedding. So I'm going to go ahead, control copy. We're going to paste it in here. All right, and now we've got our evaluate function ready. So the evaluate function takes my pairs list, so the data itself, and embeddings is going to be the object that does the embedding. We need to instantiate an object that will take sentences and create embeddings. So this is the list of the pairs. So this data here, similar and dissimilar. And then we need an object to do the embeddings. So the evaluate function evaluates embeddings for a given list of sentence pairs. So what we do is for S1 and S2 in my pair list, right? So let's say we grab similar. So I would grab these 2 sentences into S1 and S2. And then it runs them through sentence and through sentence here. So sentence is this object here. And then once we have that, we proceed. So this will probably do some kind of subword extraction. So like a sentence piece or the other ones, byte encoding, etc. All right, so we get the tokens S1 and S2, and then we're going to apply the embeddings object, which is going to vary. We're going to try several ones to take the S1 and S2 and convert them into the corresponding embedding. So if you look here, okay, and then after that, we should be able to just run S1 and S2 on the similarity function, get a score. We also have a list of scores that we accumulate, and then we can send out the list of scores for all the sentences, plus a mean of the scores so that we have one single value. Does this make sense, guys? Any questions?
No questions, it's making sense.
All right, perfect. All right, so now all that remains is these 2 functions will be used for every scenario, right? So we'll now start with the first scenario. So let's go ahead and do that. So I'm going to call, so after evaluate, we're going to call the first scenario. The first scenario is based on glove. Go ahead and call glove. So you might ask, so what is glove? So glove is a type of word embedding, like word to vec, but it's basically a set of pre-trained vectors that were created from a very large, very large corpus. So that whenever you get a new word or you get a word, you just use those vectors. Instead of you having to create your own vectors from scratch, you just use the glove vectors. Okay, so so here we have average word embeddings with glove, right? So the idea we're going to use very conveniently here, Flare, which is the Facebook library. So from flare.embeddings, we're going to input word embeddings and document pool embeddings, these two objects. So from word embeddings, we just instantiate the glove object, glove embedding. And then we say that we call the document pool embeddings, right? And we specify that we want to use glove embeddings. Now we have this object, glove pool embeddings, which is basically the object that will convert the text into glove vectors. So you can see that here. So here we have glove pool embedding. We're passing that to the evaluate function, and we're also passing the similar text and the dissimilar text. So what this should do is it's going to basically run through the evaluate function, right? Calculate the similarity between all sentences, accumulate them in a list of all the pairs, and then calculate the mean. So we'll have a mean of the similar and a mean of the dissimilar, and then we should be able to compare to see if glove is actually accurate or not. Okay, and that's basically the idea. Okay, so let's go ahead and run this, see how it performs. Should be seeing the prompt now. So I hit enter. Okay, it's doing something. And there it is. It worked. Right, so if you notice, actually, there are about 4 or 5, right? There's 5 entries. So that means there's 1, 2, 3, 4, 5. 1, 2, 3, 4, 5 for similar and dissimilar. So the first one is similar, and the score is 0.98. And then the second one is dissimilar, and the score is 0.94. If we look at the individual sentences, it's saying that a black dog walking beside a pool and a black dog is walking alongside the pool are basically 97% similar. But it's also saying that for the dissimilar ones, a little girl and a boy are reading books and an older child is playing with a doll while, whatever. It's saying that those two have a similarity of 0.94. So although it is less, it's actually still in the 90s. Do you see this, guys? That the cosine is not actually perfect here when using glove vectors. It might be a little bit better, right? I mean, it's kind of correct, but it's pretty close, right? Do you guys see that? Does that make sense?
Yep.
All right, great. Yeah, so it kind of doesn't, but we probably you probably expected, for the similar ones to tell you it was high value, for the dissimilar ones to tell you it was a low value, and it didn't. So maybe we can do this a little bit better. So how about we try another technique? So the next technique we're going to try. Now remember, this just pretty much took a word. You have the pre-trained glove vectors. So let me go to the whiteboard. So in this technique, you have a set of pre-trained vectors, glove, train, let's say on many. So glove is like built on the ideas of word to vec. It was trained on a large corpus. And now you just have readily, for cat, you have a vector of size n, and then you have for plane, a vector of size, n, and so on, right? So all you're doing is a lookup of these, and then basically in the sentence, you just average them, okay? So like, if we go to this one over here, so a little girl and boy are reading books, it would grab the vector for a vector for little, a vector for girl, and so on, and it would basically just average them out, and then that's how it calculates things. So that method does not seem to be so great, okay? But let's try another one. So we're gonna go now and try GRU. I'm gonna go ahead and just copy this one. GRU is another technique, basically. GRU. Okay. So here we have it. So basically, this one considers sequence, but it's an RNN-based technique. So what that means, it's a recurrent neural network. So for this one, sequence is really important. Okay, when it does the embedding, it's doing the embedding in such a way that it can, it considers that this word follows the previous word and that word follows the previous word and so on. So the algorithm is more, it considers sequence. Once again, we go to Flare from Facebook, flare.embeddings, and now we import, again, word embeddings, just like before, and the document RNN embeddings. And then we create the object document RNN embeddings with a why glove? Do I have an error here? Let me just confirm this because that would be exactly the same thing we did a second ago, wouldn't it? Okay. Yeah, so this, I think, what do you guys think? This should not be like that, correct?
We're still seeing the whiteboard.
Huh?
We're still seeing the whiteboard.
You're still, oh, I'm sorry. Yeah, if you look at my code on GitHub, I don't think I use GRU. Following, assuming Facebook was consistent here, there might be an error there because it should be GRU. Should be glove embedding, so word embedding. Word embedding. I would say GRU here. I don't know if it's lowercase or uppercase, but we'll have to look this up. And then this should be then GRU embedding. And then in document pool embedding, should be GRU embeddings. And then this should be GRU pool embeddings. I guess I missed that. All right, group pool embeddings like that, and then yeah, this would be GRU pool. Embeddings. Right? You guys see what I'm saying? So this is lowercase. Lowercase. I'm going to go ahead and save it. Let's see if this will run. How do you clear on the Windows side? All right, so run it. Ah, didn't like it. Okay. How about uppercase? Nope. Okay. Give me a sec.
In the book, they have where it's document RNN embeddings, they still have it glove embedding inside there.
I know, but if you look, that's exactly what the other thing is, right?
I see what you, yeah.
Well, is it though? Because isn't it document RNN embeddings, and then the other one's document
Oh,
pool
is that what it
embeddings?
is?
I think so.
Yeah. Okay, good catch.
They're just like being kind of lazy with the naming.
Yeah. That's what it is. Good catch. Good eye. So this is, so you're right. So I think it was right then, right? It was correct.
Yeah, we could just change like glove embedding to GRU embedding.
Yeah, so
to
we
be
can,
clear.
so basically the RNN embedding is using recurrent neural networks instead of averaging. But yeah. Good catch there. All right, you're right. So I got mixed up completely. All right, so let me yeah, delete that. And we can just copy it. Thankfully, we just have it here. Good eye. So as you can see here, so the difference is in the previous one, this document pool embeddings just averages things, right? But still uses glove embeddings. Whereas in this one, we don't use document pool embeddings, we use document RNN embeddings, but we're still using the glove embedding. So that makes sense. So that creates GRU embeddings, which basically now it'll consider sequence as it's doing the prediction. Yeah. Is this clear for everyone? All right, so I'm not hearing any questions. So it sounds like it's clear. All right, so then, yeah, that should be it. So it was correct. Good. Am I missing anything else? Okay, so now we have then the technique, just average pooling, and then we've got the technique with RNN embeddings, but still using gloves. So now we can go ahead and run it. So I'm going to save it. and I'm gonna run it here. All right, so there we go. So now we've got just average embeddings here, and this is the one that considers recurrence. If we look, they're both average 98, 94. This one's 99, this is 88. It's a little bit better. Look at the spread. So here was 97 to 94. Right now it's 99 to 88. So the similars are more similar, the dissimilars are more similar, but these are two pretty much the same. This one's less of a spread. This is more of a spread. So it's kind of all over the place. Okay. But it kind of gave us this. So although it's a little bit better, it's not so great. Would you agree?
Yeah, could you show us the output?
Oh, did I not? Oh,
Yeah, you're sharing just Notepad.
yeah. Sorry about that. I need to, I thought I was on the one that shares everything. Do you see it now?
Yep.
Okay, yeah, sorry. This is what I wanted to show you. Yeah, so you can see here, the GRU embeddings are not that much better. On average, they're pretty much the same. Some of them have a bigger spread, but not really consistently. They're both using glove. This one averages them. This one considers recurrent. So it takes into account the previous word given the current word. All right, so those have been a little bit disappointing. Let's try a few more. So we're gonna try a BERT model now, okay, for embedding. So we're gonna go ahead and try that. I'm gonna go here. Now you guys can see the code, correct?
Yes.
Okay, perfect. All right, so now we've done RNN. Now we're gonna go over here. I'm gonna copy this section of code. And now we're using a transformer, whereas before we were just using standard embedding approaches like word2vec, etc. Here we're now getting into transformer. So that the following execution instantiates a BERT based on case model. So whenever you see base, it just means whenever they build a transformer, there's always usually like a BERT base and a BERT large. And the base is just smaller than the large one. Less data, less architecture. On case just means that they ignored uppercase and everything was lowercase. And basically this model pools the final layer. So what that means is that the tokens are represented by the embeddings in the final layer. So if we go to here, the whiteboard, what that means is, remember, a BERT model is a large stack of embeddings, right? Just like a neural net. So it's like, you know, all the layers and attention mechanisms and so on. You give it the input, a sentence, and it's going to encode and encode and encode and encode and encode. And really, you could grab anyone and it would be an embedding, right? But the idea is that if you grab the last one, you know, in theory, that's gone through all the other layers. So that could be the best embedding for that sentence, right? So that's what that means. So if we go back to our code here, then we have the following execution instantiates a BERT based on case model that pools the final layer. And this is a non-specific BERT, so basically not a fine-tuned BERT, but just a general BERT model, right? Usually these are not better than Word2Vec because it's just the BERT model for which pre-train on all the data based just on the two ideas that BERT uses, which is mask token prediction and next sentence prediction. All right, so if we look at this, we call from flares.embeddings, we import transformer document embeddings, right? And then transformer document embeddings, we just tell it to use BERT based on case. I think if you guys run this for the first time, it'll download this model in a very similar fashion to how Hugging Face does it. Just keep in mind, this is Flare, Facebook. I'm not sure if this is downloading directly from them or it's downloading from Hugging Face. So just be aware of that. And then that creates your BERT embeddings object. So this is a BERT non-specialized embeddings. And you'll notice that it is not better than GLOVE. Actually, it'll be a bit worse, which kind of proves that the general pre-trained BERT without fine tuning is not better than normal word embedding. So then we give it the BERT embeddings, similar and dissimilar, and we're going to run it. So hopefully this will run. Okay. It's thinking. Okay, great. So we've got some results, and you can see that the difference is 0.90 for the similar, 0.92 for the dissimilar. This is
We're
actually
only seeing Notepad again.
Huh?
We're only seeing Notepad again.
Really? Why do I keep doing this? Okay, do you see it now?
Yes.
Okay, sorry about that. All right, so again, I was in the code. I did this one, right? And then now I ran the code, so you should be seeing it, and you see the output. So actually, the BERT non-specialized embedding, just the BERT without fine tuning, just a pre-trained, gives you really bad results. Actually, it's saying that the dissimilars are on average more similar than the similar. Do you see that? Any questions on this one? No questions? All right, so now we're gonna try okay, so we just tried the BERT non-specialized. So now we're going to try something called sentence BERT, which is a specialized BERT for this task. So a similarity. So this has been pre-trained, okay, for this task, and let's see how it performs. This one actually ran for me first, and then it gave me stop running for some reason, because I think the server was down. I hope the server is not down currently, but let's try it. Oh, sorry. This was the non-specific BERT. Now we're going to try sentence BERT, which is a specialized one. Copy. Okay, so if we take a look, this is sentence BERT. Now, are you seeing the code?
Yep.
Now you're seeing a specialized BERT for this task from Flare, from Facebook, flare.embeddings, import sentence transformer document embeddings. Okay, so this is a specific one for sentences. And then we create SBERT embeddings, which is sentence transformer document embeddings. And we're going to need to import BERT base NLI mean tokens. Okay, so that's a specialized one. This one, according to my results, if it runs, should give us better results. I know this gave me an error yesterday, but I had been able to run it like last week. All right, so notice this one actually does what we want. We call SBERT embeddings for similar and dissimilar. Let's go ahead and run this one. Hope it works. Ah, yes, it worked. Great. So the server was just down, I guess, yesterday. Perfect. If you guys notice this one actually does what we want, right? Notice that now for the similar ones, the average was 97. For the dissimilar ones, the average was actually 21. Perfect. Perfect, perfect, perfect. So you can see here, it's saying that for, for the similar ones, 98, 95, 96, 99, 98. For the dissimilar ones, 48, 41, 19, minus 0, 5, and 0. That's amazing, right? Wouldn't you guys agree that this is nice, that it works really well? Any comments or thoughts?
Which one was that?
Hmm?
What was the name of this one?
This one is the last one that we did, which is the, can you guys see the code?
Yeah, we can see the code.
So what we've done so far is we did glove, just average pooling, right? Which basically means we take the words, we convert each word to the glove equivalent vector, then we average them in the sentence, and we calculate the similarity. That didn't work so well. Then we did GRU, which still glove embeddings, but we call an RNN model, which considers sequence in the model, but still didn't do so well. Then we tried BERT, a non-specific BERT. So just remember that whenever you have a BERT model, you do the pre-training and then the fine-tuning. So this had no fine-tuning, just the pre-training. Actually did really bad, worse. But when we took a sentence BERT, a specialized BERT for this task, it actually does really well. So this is, to answer your question, this is SBERT or sentence BERT based on this model. Does that answer your question, Jason?
Yeah, I see that.
All right, so this is, so that one worked. So let's do this. It's 3:40. Let's take a 10-minute break and we'll start at 3:50. This is a good stopping point for this video. And then after this, we're gonna do a quick recap and then do the same exercise, but now with tricky sentences, not with similar, dissimilar. So let's take a 10-minute break and we'll come back at 3:50. Okay, guys?
Got it.